Hi guys! This is the third part of the three-part lecture on the topic Applied Maximum and Minimum Problems. In this video, we are going to be discussing two advanced problems. As usual, on the left side of the screen, we are given the steps in solving absolute extremum problems and the steps in solving optimization word problems. Now without further ado, let's begin. For our first problem, Angelo, who is in a rowboat 2 miles from a straight shoreline, notices smoke billowing from his house, which is on the shoreline and 6 miles from the point on the shoreline nearest Angelo. If he can row at 6 miles per hour and run at 10 miles per hour, how should he proceed in order to get to his house at the least amount of time? In this problem, Angelo sees smoke billowing from his house, indicating that his house is possibly on fire. That's why he wants to go to his house in the least amount of time. He has two modes of travel or transportation. One is by rowing, the other by running. When he rows, he will have a shorter distance traveled but will have a smaller rate of travel. On the other hand, running will have a longer distance traveled, but he will be faster when he is running. This is a standard transportation problem where you are given two types of transportation. One will have a shorter distance, one will have a longer distance, but the one with the longer distance will be faster in terms of its average rate compared to the one with the shorter distance. It's basically trying to balance how to prioritize whether the rate or the distance. For example, if we wish to go from Math Building to Melchor Hall without a car or a bicycle, two possible scenarios are as follows. One, you ride the ECOT Jeep until Melchor Hall, and another is you walk the whole way. Walking the whole way will be shorter, but it will be much slower compared to the average speed of an ECOT Jeep. But the ECOT Jeep will be faster. At the same time, it will travel a longer distance. In this way, possibly combining the two transportation will give us a shorter time. For example, if we walk from Math Building or we ride the ECOT Jeep from CS until AS, and then we walk from AS to Melchor Hall, that will give us a shorter time. We see here that combining these two types of transportation will give us or will lead us to a short amount of time. It's exactly the same principle that Angelo wants to employ in his predicament. Of course, in a real-time scenario, you are not going to be computing all of this when you see your house on fire. But we are going to be assuming that Angelo is a very, very bright student of Math 21 who can solve optimization problems instantaneously. There are a lot of problems in this example. The first one is understanding it properly. As you may see, there is no sort of orientation in this problem. And when I mean orientation, we don't know if Angelo is on the right of the house, on the left of the house, and so on and so forth. This is because it does not matter. The only thing that matters are as follows. 1. We have a shoreline. 2. Angelo's house is on the shoreline, and Angelo is starting on a rowboat, which is of course in the sea. We also know that from the starting point to the shoreline, that will be 2 miles, while from the point closest to the starting point to Angelo's house, that will be 6 miles. However you orient this, as long as it will look similar to this one, we will be able to solve the problem. Now, the question now is, how do we proceed? Now, proceeding means the following. I will be starting in this point, and either I row from this point until my house, or I will be rowing from this point until this point here, and then I will be running. Or possibly I will be rowing from the starting point until some point here in the middle before I run. Now, since Angelo is a bright student, we will be assuming that we will remove all other extraneous cases. For example, the case where Angelo will row from this point until some point here. This is definitely not optimal. Also, rowing from this point until another point here before running is also not optimal. Another non-optimal solution is rowing from this point and then curving until some point here. Of course, the shortest distance from the starting point until a point here is a straight line. We will also be assuming that we cannot walk on the water, so we need to first go to the shoreline before we can run to Angela's house. And thus, the important question here is, where do I go in this line segment before Angelo starts running? Let's see to be that point, to be the distance between this point, the point closest to the starting point, and the point where he will start to run. Now remember, after this, we need to know what it is we need to optimize. In this case, I need the least amount of time. So I need to minimize the time. Remember that the time travel is just distance over speed. Since I will be combining these two transportations, I will combine this total time traveled from this point until this point, plus the total traveled from this point until Angela's house. So, the total time from that I rode is basically this distance here, which in this case is just the square root of 4 plus c squared, the distance of the length of the hypotenuse, over 6, which is the rate of my rowing, plus the length from this point here until Angela's house, which is just 6 minus c over 10, which is the rate of running. Now we have the function p of c. This is a single variable function, so we can now proceed in finding our interval. Now, as I've told you, since we will be removing all the extraneous cases, the best possible scenario here is that this point will be from between Angela's house and the point closest to the shoreline. In this case, the value of c will range from 0 to 6. Notice I included 0 and 6 because for all we know, the best way is to row from this point until the house. Or possibly running is the most optimal way, so he needs to first go to the shoreline and then run. This is a closed and bounded interval, and that means I can try to use our first technique, which is the one reliant on the extreme value theorem. So I first find critical numbers of f. Unfortunately, the second problem of this example goes with this part. Because of the square root, when we try to get the first derivative of t, we will obtain this quantity here, which if we simplify, will have a radical in it. And since I need to find the critical numbers, ergo the zeros and the undefineds of this function, I will be forced to add these two fractions here and ask myself, when is this 0 and when is it undefined? This will never be undefined because the denominator will never be 0. On the other hand, this will be 0 if the numerator is 0. And this will give us a radical equation, which will be solved as follows. I will be transposing this, square, simplify, transpose again, and then if you factor out 4, then we will obtain two factors here, which is 2c minus 3 and 2c plus 3, giving us two critical numbers, 3 halves and negative 3 halves. But again, you need to remember that whenever you have critical numbers, you need to only consider those in the interval. In this case, since negative 3 halves is a negative number, we will be only considering 3 halves. So, as you can see, this is a little bit tedious because the equation that we solve is much more difficult than the equations that we had before. Not particularly difficult, but it requires some algebra and time to do. Now, the third part and the last difficult part of this problem is that even after you got a single critical number, and we are now going to evaluate, the evaluation and the comparison are not entirely easy. For example, if you evaluate the endpoints 0 and 6, and the critical number 3/2, I will have this fraction, and I will be forced to compare them. Now, since I need to minimize the time, I can remove the things that will make it big. For example, if you observe 4/15 is something less than 1, and 52/60 is also less than 1. However, square root of 40/6 is a number greater than 1 because square root of 40 is bigger than square root of 36, which is also 6. So we can remove 6 from our choices, and it's a matter of asking which is bigger, 14/15 or 52/60. But this is easily solved by just multiplying the numerator and denominator of 14/15 by 4. That will give us a 56/60. That will tell you that 52/60 is the absolute minimum value, and the way to proceed is that Angelo must row up to the point 3/2 miles from the shoreline closest to it, and then running straight to his house. Now, before we go to our last problem, let's have a few remarks. The first remark is something exhibited by one of the problems in the second video, and that is, the choice of the variable for the function sometimes yield different solutions, but will give the same conclusion. Unfortunately, these solutions can have different degrees of difficulty. We saw this in the cone cylinder problem, where the choice of H or R will give some degree of difficulty if we chose to isolate the variable R. But this remark will be very evident in our last example, where the choice of the variable will give a big difference in the degree of difficulty of the solutions. Another important remark is the following. Now, if I have an increasing function g, I can talk about the maximization and the minimization of a composition. Now, g of f is the case where we evaluated f inside the g. And it says that to maximize this composition, this will be implied if the one inside, or in this case, the argument f, is maximized, or the maximization of the interior function will imply the maximization of the whole composition. This is easy to see because when you have a increasing function that looks like this, for example, this is g, we see that the bigger y value is provided by a bigger x value. It means if you make x big, g will become big as well. So in this case, g of f will become bigger if f in itself will become big. This is true for an increasing function. Similarly, to minimize g of f, this will be implied by minimizing the argument f. This is opposite when you have a decreasing function, and that is, if f is minimized, then the composition will be maximized. So it will be switched, and maximization of the argument f will imply minimization of the composition g of f. This will be useful in our last example. Now, without further ado, let's have our last example. I need to find all points on the parabola with the equation x is equal to 2y squared that are closest to the point 10, 0. In terms of the first two steps, this is quite easy because the graph of x is equal to 2y squared is simply a parabola facing to the right with vertex at the origin, and 10, 0 is a point in the x-axis. Now, it is wrong to say that the point closest to 10, 0 is the point directly above it, because as you may know, in a circle, the closest point to, in the graph is actually the point, if this is a circle, that will give you a right angle with respect to the tangent line. Unfortunately, this is not a circle, so it will be harder to prove as well as to solve for the tangent line. So what we will be doing will be the following, which is I will identify what I want to be optimized and then proceed with the technique that we have learned before. So one thing to know is that the variables are also very easy. I can just let xy to be the coordinates of the desired points. Now notice that there is a relationship between x and y, which is x is equal to 2y squared. So I can choose between using x or using y. If I use x, then I will need to simplify or to express y in terms of x, and that is, I will solve for y in this equality here. In that case, y will be equal to plus minus square root of x over 2. In that way, everything will be in terms of x. If the quantity to be maximized here is related to the word closest. Since I need the point closest to the point, then what I need to minimize here is the distance, because it's the distance that gives you how close or how far 2 points are. In this case, the distance between the point xy and then 0 is exactly square root of x minus 10 squared plus y squared. I can express this all in terms of x by noting that if I divide both sides of this equation by 2, y squared is just x over 2, and I'll have this. This is not a bad function. Unfortunately, whether the interval that we will be getting later is a closed and bounded or not, I will still need to get the derivative of this function, which is a little bit tedious because of the presence of the square root. But since, by the remark before, the square root function is an increasing function, so if I want to minimize this, then that's the same as minimizing the one inside, which in this case is x minus 10 squared plus x over 2. So instead of considering this small d of x, I'll just consider this capital D of x, which is just the argument of the square root before. This is much easier to solve because this is a polynomial and also a quadratic function. Now that I have a function, I can talk about the interval. Now, I'm looking at the values of x in my graph. Since xy is in the graph, I'll look at what the values of x we are considering, and that's clearly from 0 to positive infinity. I can include 0, or I can also opt to not include it. Both of those things will not matter since I will be using the second case, which is the single relative extrema case in this problem. Now this is in terms of x. If it's in terms of y, it will look much better in the eyes, primarily because x is equal to 2y squared, and thus we will have the following here. In terms of finding the distance, it will be very much similar to before, and we can just look at what the argument is. In this case, will be 4y squared, 4 to the 4th, minus 3y squared plus 100. And in terms of constraint, since the y values in the whole curve, this will extend indefinitely downwards and this one will extend indefinitely upwards, I will not have a particular constraint aside from y being a real number. Now, if you look at them, you'll see both of the two cases will be very similar. But because of the this being a quartic polynomial, this will have a problem when you get its derivative, and we will see that later on. So let's have the first solution. What will happen if this is in terms of x? Now, as I have discussed before, if I will consider this function capital D of x and my interval 0 to positive infinity, which is not a closed and bounded interval. So again, I will hope for the single relative extrema case. To do that, I will get the critical numbers by getting its derivative. Now notice that since capital D of x is a quadratic function, its derivative is linear, and a linear function will only have a single zero. In this case, 39 over 4. And since this is a positive number, we have a single critical number on our interval. This is a good indicator because we want a single relative extrema. This is not yet done. We need to test this, so I will use second derivative test and see that when you evaluate 39 over 4 on the second derivative, this is clearly a positive number, which tells you that this is a relative minimum, and since it is the only relative extremum, we also have an absolute minimum. And thus, solving for the y, so if I plug in 39 over 4 in x equal to 2y squared, I will have a y equal to plus minus square root of 39 over 8, giving me 2 points as the points nearest 10, 0, which makes sense because I have a point at some point here, and because of its symmetry, the same point here will have the same distance. Now this is the case when you are in terms of x. If you are in terms of y, the solution will be very similar. I will minimize the argument with the constraint y in R. Unfortunately, because this is a quartic polynomial, when you get its derivative, it becomes a cubic. And a cubic polynomial can have at most 3 zeros. In this case, it will have 3 zeros, all of which are in the constraint y in R. Now, this is a little bit problematic for us, but it's not it's not necessarily a big problem because we still have not yet tested. Unfortunately, if you test this using the second derivative test, you will see that the second derivative at 0 is negative and everything else will be positive. Ergo, at 0, you have a relative maximum and a relative minimum here. Now, a very common mistake is stating that because these are relative minimum, it's an absolute minimum. Remember, a relative extrema will become an absolute extrema if we were able to show that you have only a single relative extrema. In case that you don't, we will be forced to use limits. And when I mean limits, I mean I need to analyze what will happen on the endpoints of my interval. In this case, the value of my d will go to positive infinity. This will just tell us that we do not have an absolute maximum. However, to show that the absolute minimum will be square root of 39 over 8 and negative square root of 39 over 8, what I need to do is to evaluate both of this in my function d of y. And you will notice that the function d of y is an even function. It means whether you are positive or negative, it will have the same answer. So that means the value that will be given for these two quantities will be the same. Pulling all of these facts together, we have shown that we do not have an absolute max, but we have an absolute mean at both of these numbers because they have the same value for d. And then, since we need the x value as well, I will just plug plus minus square root of 39 over 8 at 2y squared, and that will give me 39 over 4, which is exactly the same answer for the case when we solved it in terms of x. Now, you see here that the solution that we have for 1 and 2 vastly differ because one needs to use limits, the other one is a straightforward solution. Unfortunately, there is no clear indicator on how to know what variable is the best. Some say it is just by experience, some by gut feeling, and some by inspection. For example, the fact that this is a quartic polynomial is already an indicator that this may become problematic. And that's the end for this lecture. I hope you had fun with this video, so stay safe and stay healthy.